And yes, baseball. Okay. Okay. So I was just thinking, we'll try to get all a little bit. We have a grand total of weeks before spring break, including this. Now, with that in mind, one of the kind of challenges about the work that we're doing in this lab is that we are trying to purify a protein. Does anyone remember what that protein, the enzyme is? Lactate dehydrogenase. You're absolutely right. For those of y'all who said lactate dehydrogenase. We're trying to purify lactate dehydrogenase. And protein purification is something that is sensitive to a number of different things, including temperature. So in an ideal situation, the best way to purify a protein is to kind of do it in one movement. So basically to have a day or two dedicated to that process. We don't have that. We instead have to space it out. Now, with that in mind, if you were to space this out and like what we did last week, we did our separations, we did our centrifugations, and we left a pellet, approximately or a very ammonium sulfate rich pellet, and there's probably some enzymes in there. Is our lactate dehydrogenase in that pellet? We don't know at this point in time because we haven't looked for lactate dehydrogenase in any one of those fractions. Is everyone good with that? Okay. Now, if I said, okay, this is great, we're going to hold on to those fractions, and then next week we're going to do column chromatography, and then the week after that, we are going to, oh wait, the week after that is spring break. So we're just going to let them sit for an extra week, and then we'll check to see if there's lactate dehydrogenase in any of those fractions that come off of our column chromatography. That would present a problem because then that protein that we've tried to purify is sitting at 4 degrees Celsius. 4 degrees is good, but there's the strong potential that the proteins that are in that mixture will basically die over time. So with that in mind, we're going to have a hard stop right now. This upcoming week, or the week that we are currently in, you're going to be doing a dry lab. So you are not going to go to your system just like baseball. Okay, it's picking something up. Okay, so is everyone kind of clear on that? I'm really hoping that my audio doesn't toast out, but I'm seeing Joel Gray, so that gives me some sense that my microphone is kind of working. So is everyone clear that they are not going to Chem 109 this week during their regularly scheduled lab time? Okay, next week you are not going. The next week is spring break, so you're absolutely not going. I think there might be trespassing charges at that point in time. So the way that I approach this is we're going to have a kind of dry run simulation. This software right here, this program, cleverly titled Protein Purification, I feel like it's very valuable because it gives you a simulation of purifying the protein or purifying an enzyme. Now, let me let you know right now, you know what I'm going to do? I'm sorry, I have to take the moment to do this because my audio will no doubt screw up because this has happened in the past. Switch to phone audio. Okay. I don't mind taking the time to do this because then I don't have to post I post a Zoom recording that has nothing on it or no audio. Nine 2 5 8 9 3 9 7 8 7. Okay. All right. So, okay, everybody. Thank you all very much for your patience on that. I just make sure that we have an audio track to this video. Okay, so you will not go to lab this week. You will not go to, but you do have an exercise that you're going to do. Now, this exercise, I like it because getting to the heart of protein. Details. Now, some of those details are important. For instance, in our class, we will talk about lactate dehydrogenase. We will put lactate dehydrogenase in a metabolic context. It's significant in that respect. But whenever you're trying to purify an enzyme, function that that enzyme has, it's important, it's relevant, but don't get distracted by that when you're trying to purify an enzyme. Instead, what you're trying to do is you have this mixture, this whole cell extract, and your enzyme's activity should be in that mixture. If it is not, is there any reason to proceed trying to purify that enzyme? No. So, and what I mean by that is this will use terminology that's a little bit vague, and it's intentionally vague because I want you to appreciate the concept. So this will refer to enzyme activity. Does it matter or what that enzyme does, what the products are, or anything of that nature? For this, it does not at all. Okay. Now, as we work through this, I'm more than happy to take on any questions that y'all may have. So I'm going to give you a worksheet where you're basically working through developing a enzyme purification scheme using this tool. Okay. And like I said, I'm recording this, so I'll post this on Canvas so you'll be able to watch it at a later date if you so choose. Now, what you're start with a number of different mixtures. Default mixture, easy 3 mixture, example mixture, and complex mixture. Now, the source, the biological source of any of these things does not matter. Easy 3 mixture has a total of 3 enzymes in it, and you're trying to extract one of those enzymes from that mixture, okay? Every other mixture in here, if we go to complex mixture, okay, that's going to ask you which protein or which enzyme are you trying to purify. Those proteins are identified. Select one protein or one enzyme to purify from this mixture, numbered 1 through 60. Does the identity of that protein matter at all for this? Doesn't. And so you can pretty much arbitrarily pick a number. 13. Wait, that's a bad luck number, I think. 30. Because I'm 9 old. Look at protein number 39. 39 matter versus any other number in here? No, it doesn't. But for our purposes, number 39 has one particular function. Do we know what that function is? We don't. Do we care what that function is? At this point in time, we don't. We just know that 39 has a function different from 1 through 38 and 40 through 60. So we want to extract number 39. Does that make sense? So we're going to click OK. And whenever we click OK, we get a little bit about our enzyme. The enzymatic activity of protein 39 is stable for several hours at temperatures up to 35 degrees Celsius and at pH values between 3.5 and 11. Now, those details are fairly broad and wide-ranging. For instance, 35 degrees, your body temperature approximately, 37 degrees Celsius. What I want you to take away from this is that within this complex mixture, it's entirely possible, if not likely, that there are enzymes that will remain stable beyond 35 degrees Celsius, maybe as high as 60 degrees Celsius. But what this tells us is that all of the experiments that we're doing, given the option, if it says select the temperature that you're doing this at, we want to do it at a lower temperature, something like 4 degrees Celsius. Because if we do it at 38 degrees Celsius, what's the possible outcome for our enzyme? To die, because it's going to, it starts with a D and ends with a denature. It's going to denature if we work at too high of a temperature. Does everyone follow me there? Okay. Now, pH ranges between 3.5 and 11. If you think about the pH scale, that's the king's ransom of that scale right there. So what we can really take away from this is that we don't want to work at a pH from 0 to 3.499 or above 11. Is everyone good with that? So this just gives us some very basic information about the enzyme that we're trying to purify. So we can take away from that. Okay. Now, this is basically your baseline information. How much protein is in that? We haven't done anything to purify or extract anything. We know that there's 960. One of the proteins in that mixture, accounting for some of that 959 milligrams, is our protein, number 39. Do we know the fraction of it? Nope, we don't. Our enzyme, our specific enzyme, our specific activity that we are concerned with, we have 10,000 units of enzyme activity. Now, when you think about and you compare enzymes to one another, if you're thinking about like a DNA polymerase, for instance, a DNA polymerase versus say so a DNA polymerase is going to make a new piece of DNA. Would everyone agree with that? Okay, compare that to hexokinase, the first enzyme in glycolysis. Are those products pretty fundamentally different? I'm going with yeah, because one of them is a phosphorylated sugar, and then one of them is a polymer. Okay, so we've got those two different types of enzymes. If you were to say, so in order to compare those two enzymes, you have to distill down a measure of their activity, which is why we use a very vague and general terminology of enzyme units. We're not defining what one unit is. We're just saying there are 10,000 enzyme units. So our enzyme, we're starting with 10,000 units of that enzyme. Is everyone good with that? I detoured a little bit just because I wanted to explain that unit is just kind of the general measure of the amount of enzyme that you have in that mixture. Does that make sense? Okay. Next up is percent yield. How much your enzyme is in that mixture? Again, we have done nothing. So 100% of our enzyme is still in that mixture. Next column is enrichment. What we're trying to do is we are trying to enrich for our enzyme. We're trying to get rid of the other junk and enrich for our enzyme in particular. Is everyone good? So that number right there, if you're looking at these first four columns, what we want is we want our protein amount to go down. We want our enzyme, units, yield, and enrichment. Because if those stay the exact same and our total amount of protein goes down, what does that tell us? Increase the purity of our protein. We've gotten rid of stuff that is not ours. Does that make sense? So the last column is cost. And that's kind of the last column there is cost, and that basically is the gamification of this. So when you do any sort of research, there's an expense, and that's just trying to make this very simple piece of software a little bit more exciting and fun. And so what will end up happening is if you go through too many or too many purification steps and your enzymes, if those go down too fast, you will get a notification that says you've been fired. So you want that cost. Basically, if you do something, you want to see that, you want to see whatever you did be worth it. Does that make sense? Okay. Now, what you're going to be working with is this next menu item, separation. The first thing up there is an ammonium sulfate fractionation. We did that. We've done an ammonium sulfate fractionation where we separate based on solubility. We separate proteins based on solubility. The next menu item is heat treatment. Do we have any information about our enzyme where we could start, where we talk about a heat treatment? Do we have any limitations for a heat treatment? We do. We know that our enzyme is stable up to 35 degrees Celsius. So if we are to take this heat treatment and adjust the temperature to 35 degrees Celsius, and let's say we incubate it for 2 hours, 120 minutes. Click OK. What we notice is that protein amount, what happened to it? Yeah. What about our enzyme yield and enrichment? Stayed the same where they went up. So when that protein amount went down, again, this column relates to total amounts of protein. Of those 60 different proteins, some of them, and some portion of them, precipitated, some of them denatured. There were some enzymes or some proteins in this mixture that couldn't stand the heat, so they got out of the kitchen. Our enzyme, on the other hand, what happened to our enzyme? Same. We were good. So arguably, we could incubate this again for another 2 hours at 35 degrees Celsius, and we really wouldn't expect anything to happen to our enzyme. Is everyone good with that? Now, this is the step, if you decide, I'm just going to repeat heating over and over again, you're going to get fired. Because the cost, you're spending time, you're spending 2 hours, and your enrichment is not dramatically increasing. Does that make sense? Okay. And that's, again, that's just kind of the game component of it. And I don't want to hear anyone getting addicted to games over spring break and this being their game. Wouldn't be very exciting. Okay, so next we're going to go to our next separation. Let's go ahead and try an ammonium sulfate fractionation. So what we need to do is we need to adjust the percentage for our ammonium sulfate by means of saturation. So last time we did a 40 and a 65. I always get them mixed up. It's either 40 and 65 or 45 and 60. I believe it was a 40 and a 65. So let's go ahead and adjust this down to 40%. And what we want to see here is, again, we want to see the total protein or our protein, that number go down, and then our enzyme yield and enrichment stay the same. Okay. So I'm going to put this at 40, and I'm going to click OK. Oh, man, oh, man. You have precipitated 47.1% of your enzyme, 27.7% of the total protein. How do you want to use the pellet, or you can use the supernatant? Look at this. Does everyone follow me? You can proceed with the pellet, or you can use the supernatant. An ideal situation would be 100% of your enzyme has been precipitated. If you get that, then some fraction of that protein, or some fraction of the total protein remains in the supernatant. It's clear where your enzyme is. It's in the pellet. Is everyone good with that? Now, in this case, 47% of the enzyme is in the pellet. That means 53% of our enzyme is still in the supernatant. We haven't really arrived at a conclusion where it's like, oh, clearly you want to go in this direction. Clearly proceed with the pellet. So this is kind of cheating, but not really. We can click cancel. Go back to separation, ammonium sulfate saturation. Let's adjust it down. Let's say 35% saturation. Okay. Well, 25% of our enzyme, again, still not particularly exciting. There wasn't
we didn't get rid of so much protein or so much non-R protein that's really worth it to proceed with the pellet, and you're sacrificing some of your enzyme if you go with the supernamed. So let's go in the opposite direction. Let's see what 45%, 62% of our enzyme, 36% of our protein. Now, there's any purification step that you do, any step in a protein purification or enzyme purification that you do, there's going to be a cost. You're going to sacrifice some of your enzymes for kind of the greater good. The greater good being enriching more and more of your enzyme. Now, we just did 45% and our amount of our enzyme went up. You know what I'm going to try? I'm going to click cancel, and let's go with 55%. Okay, so what I want you to see here is that the amount of enzyme and the amount of total protein, they're kind of going up together. They're going up a little bit hand in hand. For the purposes of proceeding, and the questions that y'all will have on your worksheet where you're walking through this are going to be, what happens when you do this? What percentage of your protein ends up in the pellet? What percentage ends up in the supernamed? For this, I'm just going to say, we're going to use our precipitated material. So I want you to think, if we're using our precipitated material, 81% of our enzyme is in our pellets, has been precipitated. So we're sacrificing nearly 20% of our enzyme. Is everyone with me there? But we're also getting rid of some of our total protein that is not our protein of interest. So what we want to look for here is, and what we want to expect is that our enzyme unit, that's going to go down. Our yield is going to go down. What we want to see is our enrichment continue to go up. I'm optimistic that it will a little bit. 1.2. Not dramatic, but there we go. Okay, so you can continue doing ammonium sulfate precipitations. Continue spinning with that same percentage and hopefully enrich for more, basically in that same ratio. But in the interest of kind of demonstrating what your purpose and your intent here is, we're going to go on to proceed to another separation technique. Now, with what I've presented so far, does anyone have any questions? So the next separation techniques are getting types of chromatography. If you look at this list, we have a total of 4 different types of chromatography. We have gel filtration, ion exchange, hydrophobic interaction, and affinity. Those are your 4 major and most common types of column chromatography used by biochemists. Gel filtration is a chromatography technique that separates based on molecular weight or based on size of a molecule. Ion exchange chromatography is a separation technique that separates based on charge. Hydrophobic interaction separates based on hydrophobicity of an enzyme. Affinity chromatography separates based on an enzyme's affinity for a specific molecule. Now, for example, if you are doing affinity chromatography and you are trying to purify an enzyme, if you're trying to purify a hexokinase, an enzyme that acts on glucose, a hexose, what you would do is design a insoluble sugar bead, which is going to make up the stationary phase of your column. And to that, you're going to affix a 6-membered ring. So any enzyme that will bind to glucose, chances are it's going to bind to that immobilized molecule. Now, if you were to compare, say, if you're trying, so you've designed this column that has that sort of bead. If you were to run hemoglobin over that column, what do you think hemoglobin's affinity for glucose is, or 6-membered rings in general? I would kind of hope that it'd be fairly low. I don't want my hemoglobin interested in glucose. I want hemoglobin interested in oxygen, so they can bind that oxygen, circulate it about your body. Now, the molecule or the enzymes and proteins that have no affinity for that immobilized molecule, they're going straight through the column. They will not slow down at all. Whereas those hexokinases, when they see a six-membered ring, they're going to say, ooh, maybe that's glucose. It might be mannose, it might be galactose, I don't know, I just want to slow down and check it out. Okay, yep, I'm going to grab onto that. And I'm going to stay there until I have a reason to leave. So these 4 different chromatography techniques, this is where I want you to kind of be looking at this in preparation for the chromatography that we're going to be doing after spring break. So what that means is this exercise, I'm going to give you a longer time frame to submit this as opposed to like, yes, due on Wednesday, a week from Wednesday. I want you all to spend some more time with this and look at the different chromatography techniques or chromatography columns. For instance, if you go to ion exchange chromatography says, what's the charge of the enzyme? And here's the charge of this immobilized stationary molecule. If you click info, I will give you this. It will give you a brief description of all of the different types of ion exchange chromatography. The biggest umbrella here is that there's cation and anion exchange chromatography. Cation exchange chromatography is shown here on the left, and that is where you're going to have a big circle representative of your insoluble sugar bead with a negative charge. That is going to be capturing positively charged molecules. They're capturing cation. So when you see a cation exchange chromatography column, I want you to think, okay, cation is referring to the molecule we're trying to capture. I always think about, is anyone a fisher person? Does anyone like fishing? You know, one thumbs up. You call the sport fishing as opposed to worming, because what you're trying to do is you're trying to catch a fish. Cation exchange chromatography, you're trying to catch a cation. Anion exchange chromatography. Well, anion exchange chromatography, you're trying to capture a negatively charged ion, and your protein or an enzyme would be that negatively charged molecule. Everyone good with that? Okay. So with that in mind, based on those descriptions, or I want you to investigate those different descriptions and select one of these columns. Let's say a DEAE cellulose column. A DEAE cellulose column description here is that's a diethyl amino ethyl cellulose column. So it's a diethyl amino ethyl molecule that's conjugated to a cellulose bead. These are granular celluloses which have been chemically modified. DEAE cellulose, which is DM cellulose, contains DEAE cellulose contains an ionizable tertiary amine group. So you're going to have it is positively charged at a neutral pH, and so DEAE cellulose is an anion exchanger. So the bead itself is positively charged, so it's looking for negatively charged molecules. So let's DEAE cellulose. The next part of this is elution. So basically, if we set a DEAE cellulose column up at a pH of 7, that is going to capture molecules, proteins, enzymes, ions that are negatively charged at that pH. Is everyone good with that? Because does a protein's charge change based on pH? If the pH goes down, what happens to the protein's charge? Chances are it's going to be a little bit more positive. Okay, so, and why is that? Because amino acid charges change based on pH. So DEAE cellulose is going to be capturing negatively charged molecules at a given pH. Now, with that in mind, the great thing about chromatography is, let's say hypothetically that we have this mixture of all of our proteins that we've already done the ammonium sulfate precipitation on. Proteins flow through and nothing gets stuck to the column, or our enzyme doesn't get stuck to the column. It flows straight through. Did we learn anything about our enzyme in that process? And some people say no. If it's capturing negatively charged molecules and our enzyme flows straight through, And I mean very like holistically, did we learn anything about our enzyme? We did. If it's capturing negatively charged molecules, we learned that at a neutral pH, our enzyme is positively charged. So anytime you do any sort of separation technique, you should always be learning something from it. It's not a yes or no, this works or it doesn't work. Instead, this tells me this piece of information based on these conditions. So if our enzyme flows straight through at a neutral pH, that means that our enzyme, with this specific column, that means that our enzyme, well, it's positively charged because it didn't adhere to the column. Does that make sense? Okay. Now, ideally, you set up a column where your enzyme will be one of a few different enzymes, not proteins. We will see our enzyme be the only one that adheres to this column. When we're doing ion exchange chromatography, chances are a little bit slim that it's only our enzyme, because there's probably a number of different enzymes that have similar charges. Okay, so we can, like, let's say hypothetically that our enzyme adheres to the column. We can elute our protein by either adding a salt, like sodium chloride, or adjusting the pH of that salt. So I'm going to go ahead and select a pH gradient. So what that means is I'm going to wash my column various pHs. So because as our pH changes, so too does the charge of our enzyme. Is everyone good with that? So if our enzyme adheres to our column at a pH of 7, and then we up the pH to about 10, will our enzyme have the exact same charge at 7 and at 10? It will not. So if it does not have the same charge, maybe we're making it more negative or more positive to get our protein to elute from that column. Is everyone good with that? Now, before I click OK, when thinking about a pH gradient, does our enzyme have any pH-related parameters that we have to be respectful of? What are they? 3.5 to 11. So when I select pH gradient, I'm going to click OK. And then what I'm going to do is I'm going to say my pH buffer is 7, because I know my column will be positively charged. Now it's going to ask me, what's the start of my gradient and what's the end? I'm going to have this start out at a pH with 5, have it go all the way up to 9. Okay. So what that means is I will have a solution flowing over this column. First, the pH of 5. Would my enzyme still be active at a pH of 5? It would. Do I know anything about the charge of my enzyme at a pH of 5? But this technique will help you learn that. pH of 5, then it will jump up a little bit to 5.1, then to 5.2, 5.3, 5.4, 5.5. And based on those pH changes, my enzyme should, in theory, change charge gradually. Is everyone with me there? Okay. I'm going to click OK. Here's what I get. Before we start talking about this, before we look at the guts of this, I want you to know this is referred to as a chromatogram. It's a graph representing your chromatography data. On our y-axis, we have absorbance of 280 nanometers. Why would we measure A280? Our tryptophans, our aromatic residues. That's an indication that we have protein here. Okay, our x-axis, fraction number, ranging from 0 all the way up to 125 fractions. So each one of these fractions corresponds to about 1 milliliter of solution. So basically, you have a test tube or a microcentrifuge tube underneath that chromatography column, and you collect about 1 milliliter, then you move to the next one. Collect about 1 milliliter, move to the next one, move to the next one, so on. So you're collecting all of these fractions, measuring A280 to see if you have protein there. And then, everyone goes with that so far. Now let's talk about the guts of this. We have a blue line, and then we have kind of a magenta line. Our blue line is represented on here. Protein. Our magenta line is representative of buffer conditions changing. Our buffer goes from where we started, 5, all the way up to, here it shows at 8. Stop there. Oh, we said 9. We did say 9. Okay. Now, with that in mind, if you look at this baseline right here, the first roughly 32, 33 fractions, the pH here is approximately 5. Does everyone agree with that? Then if I pick the point right here, the pH of our buffer here, is it still 5? No. Anyone want to guess what it is roughly? 6, 7. I like those guesses. Okay, because this represents the pH of our buffer gradually increasing. Now, with that in mind, lots of our protein is eluted from this column at what pH? 5. We don't know the exact pH here, but very early on, at a pH of, let's call it 5.3, 5.4 roughly. We have more. Looking at this information, I would say 100% of your protein eluted before a pH of 6. Would everyone agree with that? So understanding that component of a chromatogram is very important. Now, what this tool allows us to do is it has this column or this menu item of assay enzyme activity. We assay enzyme activity, so when we click that, that's going to give us another line that overlays either of these and gives us more information. Tried to say insight and information in one word, and I got insight. It's going to give us more insight into where our enzyme is. Now, do we have any information as to where we can get our enzyme? Well, it's either here or here. Would everyone agree with that? We have no other information because we can't really extract anything from pH. So I'm going to select assay enzyme activity. Boom. 10 through 30. Yes, good thing. 10 through 30. That's where our enzyme is. So our enzyme is eluted from our column at a pH of 5. These fractions, number 40 through 47 roughly, this second peak. Do we care about the proteins in that peak? We do not care about those at all. Now, with that in mind, this early peak right here, can we say anything about the purity of our enzyme in that fraction? Yeah, we can't say that, oh, well, this is 100% of our enzymes, and this is 100% of junk. We might be looking at, this is 1/3 our enzyme and 2/3 junk. We really do not have enough information in order to process that. So if you were to be doing this in a lab setting, what you would do is you would collect those fractions. Fractions number 10 all the way up to 30. Would you be able to say anything about the charge of our enzyme base column? Now keep in mind, the charge of our column at a neutral pH is positive. At a tertiary amine. So it's going to be positively charged at a pH of 7. It's going to be positively charged at a pH of 5. What would you say our enzyme, in this bunch of proteins there, what would you say the charge of our enzyme is at a pH of 5? Since it basically went straight through the column. If it went straight through, it didn't adhere to the column at all, our column's positively charged, nothing slowed, gas, no brakes. Our protein was positively charged. These proteins right here, this peak, more positive or more negative? These proteins right here between numbers 40 and 47, those bound to our column, and at a pH of 5, those did not elute. But then when we got our pH a little bit higher, then they finally did elute. Does that make sense? So these proteins have fewer positive charges than these. That's one way that you could look at that. Now, does anyone have any so far? Talk about your ammonium sulfate and heat separations. If you get a protein that's referred to as thermostable, something that's good up to about 60 degrees, man, oh man, that's my dream sort of protein. Why? Because you can leave it on your bench when you're working on it, forget it there, and then come back the next day and boom, it still works. Something that is resistant to long periods of time at room temperature. That's a good protein to work with for me, because then you can screw up and come back to it. If you're working with a thermosensitive protein, like something like this, then you have to work with it basically on ice and at lower temperatures. In this exercise, when you pick your protein number, you might have rolled snake eyes and get, a temperature, something that's stable up to 60 degrees Celsius. In which case, if you heat it to 60 degrees Celsius, what's that going to mean for almost every single other protein? Well, they're going to be heated to 60 degrees Celsius, and a lot of those are going to denature. Does that make sense? So if you're thinking about this round back to molecular biology, polymerase chain reaction. Polymerase chain reaction, what's the enzyme that you use for that? Pac polymerase. Pac polymerase is good up to what temperature? First round of your first temperature that you hit PCR at. I think I saw one person say, not 4, higher than 4. 40, it's in the 90s. 98 degrees Celsius as a tribute to the band, 98 degrees. It goes 98 degrees, drops to 55, goes to 72. It goes back up to 98, 55, 72, 98, 55, 72. That is a very thermostable enzyme. It can endure these temperature changes, these high temperatures. If you took this enzyme right here that we were trying to purify and heated it to 98 degrees Celsius, what's going to happen to it? Every hydrogen bond that keeps it intact is going to be broken. Ionic bonds that keep that structure intact, those are going to be broken. That enzyme is toast. Thermostable enzymes are kind of easier to work with in some respects. Does everyone follow me there? Okay. So after you've identified, okay, well, there's my enzyme, I've learned a little bit of a question. This one? Yeah. That represents our gradual increase in pH of our buffer. Because we started with a buffer that was at about a pH of 5 and raised it to 9. So this is the gradual increase. Whenever we did the enzyme overlay, it changed the y-axis there, but that magenta colored line corresponds to our buffer pH going up. So, any other questions? Next up, we're going to go to page, or polyacrylamide gel electrophoresis. We're going to do a one-dimensional page, and that's going to say which fractions do you want to analyze. And we'll say 10, add that. 11, add that. We'll go 20. I'm just going to pick a couple of them. Number 30, I'm jumping number 40, and 42. I will click add, and I'm going to click OK. So I selected a handful of fractions. And this shows me in fraction number 10, fraction number 11, I don't really see any protein. Fraction number 20, there's a ton of protein. Fraction number 30, there's not much of any protein. 40 and 42. If I had completely purified my protein, I would see, if I had a perfectly purified protein, I would be looking at something like this. Just one thick band. Each one of these bands corresponds to a different polypeptide. If I had purified my protein perfectly, that's what I would be looking at. So at this point in time, with respect to the purification scheme that we came up with, not particularly great. One of these, in fraction number 20, one of those is our protein. One of those is our enzyme. And you counted that out. I'll say 18. One of those 18 bands is our protein of interest. So there's definitely room for improvement. Now, can we identify which one of those is our enzyme of interest? We absolutely can by going to page and clicking immunoblot. Immunoblot is the same thing as a Western blot. Is anyone familiar with a Western blot? So it's basically using an antibody raised against your enzyme of interest to say, boom, there is your protein, there is your enzyme. So we could conclude things about our enzyme. One, it has a molecular weight that 20K corresponds to 20 kilodaltons, so 20,000 daltons. A single amino acid is about 107 daltons. Our protein is probably 250 amino acids long, based on those very rough numbers there. We could also say that our protein at a pH of 5 has a positive charge. We basically added some information for the next person doing this purification. We could say, well, it's good at this pH. It's going to have this positive, or it's going to have this charge. So if you're doing this sort of purification, do you want to use the exact, if you're passing this information on to someone else who's going to refine this purification, do they want to use the exact same column? No, they don't. Because if they use the exact same column, probably they're going to find the exact same information that you have. You want to enrich for that one protein. You got from 60 proteins, you narrowed it down to about 18 proteins, and your one protein was in that mixture of 18. So if you think about this in terms of purity, maybe that's one of 18, so yours is like 8% pure, roughly. So one out of this mixture of 18 proteins. And, you know, also, I'm not trying to say this as like, you really shouldn't feel good about yourself, because I was the one steering here. We lost some of it in our purification scheme. We did that ammonium sulfate precipitation. We sacrificed some of it because we were hoping to get more of a return down the line. Okay, does anyone have any questions about this? Like I said, I'm going to be posting the worksheet for this on Canvas, called Tracks. On Canvas later today, you have a longer window in which to work on this than you do our other worksheets. So if you have questions about this, if you're having issues navigating the tool, I'm going to share the URL with you and everything like that. Please let me know. I'd be more than happy to help you. The worksheet is really just kind of getting you to begin an exploration into how to enrich for one particular enzyme. It's not, you better get this perfect or you get a 0 on it. This is, you know, if you selected protein number 32 out of 60, it's going to give you some information about how those parameters of that enzyme. Anything that you can add to that is valuable information. We learned about the charge based on a chromatography column. Was our protein the only one that had that same charge? No, it wasn't. So hope everyone understands kind of the holistic nature of this. Any questions? No. Yes. We are not. Next week, pre-spring break, spring break. We will not be meeting a week from today at 12:30. The reason for that is because when y'all return from spring break, y'all will have your fractions that you're going to look at for catalytic activity, because, you'll have catalytic activity, and then you're going to begin your chromatography column. I just didn't want samples to sit for a month, basically, and then you work with them. Excuse me? The 8th of, no, I have to adjust that date. Thank you. Are there any other questions? Okay. With that said, it's quiz time. I'm going to stop recording.